and Lineweaver-Burk plot with examples of these three types. Let's begin. The three major types of reversible enzyme inhibition are competitive inhibition, non-competitive inhibition, and uncompetitive inhibition. In the case of reversible inactivation or reversible inhibition, the inhibitor forms an unstable, non-covalently bonded enzyme inhibitor complex that can be reversed by adding more substrates or by using reactivators. The lost activity can be regained. Whereas in the case of irreversible inactivation, often the inhibitor forms covalent bonds and binds to the active site by covalent bonding so that it cannot be reversed. The lost activity is gone forever. Now let us discuss the most important concept in differentiating these three types of enzyme inhibition. In the case of competitive inhibition, the inhibitor binds to the active site of the enzyme. As you can see, this red one is the inhibitor. So the inhibitor is a substrate analog, or which is having a similar structure to that of the substrate, so that it competes for the active site with the natural substrate. That is why it is called as competitive inhibition. Whereas in the case of non-competitive inhibition, the inhibitor binds to the allosteric site. Allosteric site is a site other than the active site. On binding of this inhibitor to this allosteric site, that causes a conformational change in the active site, causing inhibition. That is why it is called as non-competitive inhibition. It is not competing with the substrate for the binding to the active site of the enzyme. And the third one is uncompetitive inhibition. Here the inhibitor binds to enzyme substrate complex. So there is no inhibition regarding the binding of the substrate to the active site of the enzyme. Here the inhibitor binds to the enzyme substrate complex. This is a basic difference between these three types of enzyme inhibition. Now moving into the detail of each of these. Let's begin with competitive inhibition or isosteric inhibition. Let's take an example. The enzyme is succinate dehydrogenase, the enzyme involved in Krebs cycle that is involved in converting succinate to fumarate. So this is the enzyme, and succinate can bind to this enzyme, forming succinate enzyme complex and ultimately forming fumarate releasing enzyme. So there is a competitive inhibitor which is malonate. This malonate, as you can see, it is a structural analog. It is having some structural similarity to the substrate succinate. That is why it is called as isosteric, same conformation. So you can see the functional groups are same. So this malonate can bind to this enzyme. It competes with this natural substrate succinate and binding, forming malonate enzyme complex without forming the product. This is called competitive inhibition. Here the substrate, or here the structural analog of the substrate competes for the active site. Both the substrate and the inhibitor competes for the active site. This is a Michaelis-Menten graph of competitive inhibition. As you can see, this red one is without inhibitor and this blue one, number 2, is with inhibitor. Let me add 1 or 2 points on Km. On the x-axis, this is Km. On y-axis, Vmax or velocity. Michaelis constant or Km is the substrate concentration at which the rate of reaction is half. So half of Vmax, you can see Vmax by 2, this is Vmax. Half of Vmax, the corresponding substrate concentration is called the Km. Km value is different for different enzymes. It refers to the affinity of an enzyme for its substrate. It is inversely proportional. Higher the Km value, lower will be the affinity. Competitive inhibition can be reversed by adding more substrate. By adding more substrate, the inhibitor may not get a chance to bind to the active site, so that the inhibition can be reversed. As you can see, therefore, the Vmax remains the same. By adding more substrate, Vmax can be achieved, whereas the Km decreases. As you can see, here the Km value is increasing in the case of competitive inhibition. Therefore, Km increases, indicating the affinity of enzyme for the substrate decreases. So this is the Lineweaver-Burk plot. As you can see here in the x-axis, it is reciprocal of substrate concentration 1 by S. In y-axis reciprocal of velocity 1 by V. This red one is the with inhibitor, this blue one without inhibitor. As you can see, this Km has shifted from this region to this region. So Km value increases, therefore affinity decreases. Whereas in the case of Vmax, as you can see, Vmax remains the same. The intersect remains the same. Therefore, there is no change in Vmax. And the slope gets steeper in the case of the line with the inhibitor. As you can see, the slope gets steeper. So in competitive inhibition, Km or affinity of the enzyme decreases, but Vm remains unchanged. Second one is non-competitive inhibition. In the case of non-competitive inhibition, this is heavy metal mercury, which is a non-competitive inhibitor that can bind to some functional groups like SH group or sulfhydryl group. The binding is to the allosteric site. That causes a conformational change in the active site so that the substrate cannot bind to the active site effectively, thus causing inhibition. So it prevents the formation of product. Enzyme substrate complex may be forming but preventing the formation of product by binding to the allosteric site. This can be reversed by adding some reactivators to remove this non-competitive inhibitor. Heavy metals like mercury, lead, pesticides, cyanide in the case of enzyme, cytochrome oxidase, all are non-competitive inhibitors. This can be removed by using chelating agents like EDTA. And this is a Michaelis-Menten graph of non-competitive inhibition. Let's have a comparison of both competitive and non-competitive. This blue one is without an inhibitor. This orange one is with competitive inhibitor, whereas this green one is with non-competitive inhibitor. As you can see, in the case of competitive inhibitor, the Vmax remains the same, but Km value has changed. Whereas in the case of non-competitive inhibitor, this green line, the Km remains the same. As you can see, the Km remains the same, but there is decrease in Vmax. The Vmax has shifted lowerward, indicating the velocity of the reaction decreases as more and more enzyme substrate complexes are formed which are inactive. Thus slows down the velocity of the reaction. And this is the line Weaverberg plot. As you can see here, the Km remains the same, whereas the Vmax has shifted from this position to this position, that indicating that the Vmax has lowered, so there is decrease in velocity. So in non-competitive inhibition, Km remains same, whereas Vmax decreases. Now moving into the final type of inhibition, that is uncompetitive inhibition. In this case, as you can see, this is enzyme and this is substrate forming enzyme substrate complex. Here the inhibitor binds to the enzyme substrate complex, thus preventing the formation of product. This cannot be reversed by adding more substrate. This is the Michaelis-Menten graph of uncompetitive inhibition. As you can see, in uncompetitive inhibition, this blue line without inhibitor, this red line with inhibitor, the Vmax has decreased, whereas Km value binds in the case of both Km and Vmax. Here the Km value decreased phenylalanine site and compete with the natural concentration. In the case of non-competitive inhibition, in that case Km remains unchanged, whereas Vmax also decreases. The affinity of enzyme